Good morning, everybody. It's currently almost 10 p.m. and Facebook Hacker Cup is going on today. So this is a 3-hour competition run by Facebook. There are multiple rounds, so it's similar to Google Code Jam in that way. If you really do the qualification round at all, then you'll make it to round 1. And then if you advance from round 1, then you'll make it to round 2. Then there's a third round, and then finally I think there's a finals in person. So I'll definitely be doing the qualification round, and it's possible that I won't be able to compete in the other rounds. We'll see. The reason why might be something that some of you may be able to guess. I don't know if I'm allowed to say what that reason is, but it has to do with a place that I might be working. So I'll leave it at that. I have opened travel restrictions already, so I haven't read it or thought about it at all yet, and I think what I'm going to do is I'm going to just do problems kind of as if it were a live stream. It's not a live stream, obviously, because I don't want to give solutions to other people before the contest ends. That would be cheating. That's very bad. But I'm going to just do it now because I've got some free time, and then if you'd like to watch my thought process, watch me solve the problems, you're welcome to do that. Maybe at the end when I decide that I'm either, I don't know how hard these problems are going to be, but when I decide that either I'm bored, don't feel like doing them anymore, or when I solve all of them, then I'll do a quick review. So I'll have solutions to them as well. But anyway, I think let's start. So travel restrictions. So I've opened this before, so I'm not reading it for the first time, but I'm thinking about it for the first time. So right here for travelers, each airline has decided to reorganize their flights in a linear fashion. We have content, or we have company?
Understood, sir.
So, yeah, we're going to reorganize our flight routes, and they don't want to make any hub, which would work quite well if you're looking for flights. You can get anywhere in 2 edges. But anyway, you're going to make a rope instead. That's my understanding of this. So you have n countries in a sequence, each assigned a number, and then you can fly from 1 to 2, 2 to 3, etc. So, oh yeah, you can go in both directions. So you can go either +1 or -1. But some countries have additional restrictions, which is an I and an O. So if the I is no, that means you can't enter that country. And if the O is no, that means you can't leave the country. So now you want to determine which trips are possible. And then you want to output a 2D array of characters. So n is only 50. So if it's a left to right pair, you just want to see when's the first no. If it's a right to left pair, you want to see when is the first yes. But if n is tiny, I think we can just do Floyd Warshalls, and that should be fine. So we can just do a 2D Boolean array, and that can just be whether you can travel from each thing to each other thing. They're ordered 1 to n already, so we don't have to worry about that order. We just have to worry about these pairs. So that should be pretty easy to code, I think. Let's make a new project for that. This will be Facebook Hacker Cup. Alright, so I think you can name these whatever you want, because we run it locally, if I remember correctly. So this is travel restriction. Main. Test cases are all small, so we don't really need fast scanner or anything. Alright. There you go. So we have our scanner. We want to read the number of test cases. And then we just want to read n for each case. And then we're given it in a single array, so char array in equals this, out equals that. Okay, so we've got our in and out. Now we want to build our adjacency array. N by n. So now we want to see if you can travel between each adjacent pair of things. So, well, first of all, you can go from I to I. That's always true. Now for everything else, if in at I plus 1 is not equal to yes, or out at I is not equal to yes, well, I guess we want these equals, right? If they're equal to yes, if they're both equal to yes, then adjacency from I to I plus 1 equals true. And then similar thing, if in at I equals yes, and out at I minus 1, I plus 1 is equal to yes, then adjacency from I plus 1 to I is equal to true. Now we just need our Floyd-Warshalls. Alright, and now for int I equals 0, I is less than n, I plus plus. For int j equals 0, j is less than n, j plus plus. This out j from I to j, yes or a no. So let's just see whether this is right. And if it is right, we'll just submit it. It might be inverted is the thing. Oh, we need the classic case number. I don't know why all of these companies find this to be a good idea. It's just annoying. Case number plus the test case plus a colon. Alright, so yes, 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 yes. Yes, yes, no, yes. Yes, no, no, yes. Some yeses. Yeah, it looks fine. And this is like a zigzaggy path. Yeah. I think that's fine. So we did get the order right. Sometimes it's from to, sometimes it's to from. That's fine. And everything looks right here. I'm not too worried about I'm not worried about like print writer time. Although it might be helpful just to do this with files, right? So maybe we'll just make a template that does that, and that'll be helpful. Static boolean submit. It's false. So we can just do this here. Because we're going to be solving several of these problems, hopefully, unless things go terribly wrong. Good. So we'll pass a scanner in, and then also a print writer. Okay. And now we can print all of these out. So now the nice part here about this is that call that O. So now we can just use this same template for other problems, and that should be easy. Static string, static final string file name. All right. So if submit, then we want to do one of these, otherwise with the other. Okay. So this needs to be some new file. And the print writer will be some new file as well. Okay, and this will have like errors, but we don't care. Alright, cool. So if this is false, then we should be able to just run it like normal. Good. If it's true, it should crash. Awesome. So we just need to save the file, and then we should be good to go. Let's make one for downloads, and let's make another one for where we need to paste the data to. It's Facebook Hacker Cup, right? There we go. Okay. Let's get the data and submit. It's a small subset of test cases used in the full grading. Can help verify there are no obvious errors before officially submitting. Let's go. So save this. How much time do we have? Oh, we have as much time as we'd like for this part. That's very nice. Okay. Well, we'll copy this. Copy that. And paste it into here. So now we should have input.out. Okay, good. Can I get my validation, please? Let me submit. Can I have any file extension? Okay, so it's going to be documents, Java files, and Facebook Hacker Cup. When able to verify whether it's a valid text file, you may still submit it. Please double check that you've updated the correct file. Yeah, I have. I think so. Okay. It's correct for the validation input, so we can make an official submission. You have 6 minutes to run your code on this submission. Okay. Save my file. Copy this. Paste it here. And then we just remove validation. Okay, now we have the right thing. Awesome. Choose the output. Choose our source code. Wait, what? What am I doing? Whoa, this is weird. That it's got both things in here. Processing your submission. Do I get instant feedback? Submitted, but nobody knows. Okay. Interesting. Oh, maybe they don't tell me until this time is over. Interesting. Oh, okay. So this actually has stuff in it already. So this is like an old round. Round 3 old. Yeah, these are all old stuff. Okay. Oh wait, no. Oh, nope, undo that. Thank you. So I think this is fine. Let's make this my template though, so that we don't have to rewrite a bunch of this code for the next time. Yeah, I think that's fine. That's a good template. Good. So now let's do problem 2, alchemy. There have been a lot of problems named alchemy. What? Why does it not? That's a, come on, please guys. Make it select the problem by default. That's annoying. Does it fix it if we do, Okay, so I guess they just like have some field somewhere that doesn't get changed, like it's universal instead of per tab. When you switch tabs, you should definitely select the problem, I think, but maybe not, whatever. Edgar and his younger brother Alfred are alchemists in the source of legendary Philosopher's Stone. The Philosopher's Stone, also known as the Red Stone, the fifth element in the elixir of life in liquid form, is a powerful alchemist substance rumored to support the transmutation of... Okay, can we get to the actual problem, please? Edgar is hoping to use the stone to restore his brother's body in its original form, following a terrifying human transmutation accident. It is known that the Philosopher's Stone breaks apart into an odd number of shards when they're used up. When the shards are used up, or when the stones, when the stones are used up. After searching far and wide, he's collected N shards of what he believes to be a previously used Philosopher's Stone, where N is an odd integer. He believes that fusing these shards together will yield a real stone in its entirety. Leveraging his encyclopedic knowledge of alchemy, Edgar recalls an ancient book with the following ritual for fusing shards. Arrange N shards in a row, 1 to N. Note the color, Ci, of each shard, which is either auburn or black, A or B. Choose a consecutive sequence of 3 shards, remove them from the row, and fuse them together into one new shard, which is the majority. Okay, they can't all be the same color. They must be 2 differently colored shards. In other words, third shards will be equal to the most common color. Yes, okay, the majority. Place the resulting shard back into the original gap in the row with the remaining shards, blah, blah, blah. Repeat until only 1 shard remains. Note that steps 2 and 3 are performed. The number of shards decreases by 2. Therefore, given the initial number of shards is odd, each successful repetition will result in exactly 1 final shard, the Philosopher's Stone. Help him determine whether or not it's possible to get to that point and save Alfred. So all that matters is the counts. Man, this was like the longest problem. Okay. 99999. What? I don't get it. Are they gonna really do me? Oh, because 100,000 is even. That's why. Explains it all. Yeah, so all that matters is the counts. You just want to see, is there one more A than B or one more B than A? Very good. This will be alchemy. How do you spell alchemy? Alchemy. Okay, get ready for the hyperbanger. N equals this. Char array line equals this. Int count equals 0 for char C in line. If C is equal to an A, count plus plus, else count minus minus, this out, count equals, well, boolean works equals math.abs count is equal to 1. Plus works, yes, or was it y and n? Y colon n. All right, give me the input data. Yes, no, yes, no, yes, no. Give me the solution data. Alchemy validation input.txt. Here you go. Submit equals true. Make my answer for me. Got my answer. Upload my answer. Validate. Passed. Give me my full input. Thank you. Put that here. complete validation. Give me my data. You can have your answer now. And here's my source code. Oh, it will be revealed when the contest ends. I see. So that makes sense. All right. Problem C. Every year, millions of logs are sent floating downstream in the Great Canadian Log Drive. Is this an actual thing? Well, if I watch this and it has the audio, I might get copyrighted. So I will look at that after contest. But apparently, oh, maybe it's a Wikipedia. Great Canadian Log Drive. DuckDuckGo is amazing because it lets you do this. So it looks like the Great Canadian Log Drive is not an actual thing, unfortunately. Anyway, as every Canadian knows, you can't have successful log drives without logs. The first step in logging season is to fell a great number of trees, taking care not to pile the trees up in a way that would make them hard to move. Ava? Wait a second. Is this the same Ava as Codeforce's Ava? That would be funny. Ava has been assigned a section of the forest with N trees standing in a row. Looking at them from the side, modeling them from the ground as a number line, the ith tree is at this position and has this height. Oh, they're in a row. Okay. All the trees are at distinct positions. Each tree may be cut down in such a way that it falls either to its left or to its right, or it may be left standing. It's important to farm trees sustainably. If the ith tree is cut down, it will form a timber interval of this thing on the ground. Well, if it's cut to the right, it forms that interval. Inclusive. The trees are cut down and will be moved to a nearby river to begin their long journey to the mill. It's hard to move a tree that has another tree on top of it, so Ava will not cut down trees in the way that would cause the intersection of any pair of timber intervals to have positive length. It's fine for them to intersect at an endpoint. For example, one tree may be cut down to create a timber interval of this, and another may be cut down to create a timber interval of this. It's also fine for timber intervals to overlap with trees which have not been cut down. Uncut trees are essentially ignored. A combined timber interval is an interval where each point within it is at least one timber interval. A combined timber interval is an interval where each point within it is within at least one timber interval. What does this mean? For example, if we combine AB and BC, then AC is a combined interval. Sure, Ava would like to form the largest combined interval possible that represents a series of trees that can all be pushed into the river at once. Determine the maximum possible length that a combined interval could have if Ava cuts down trees optimally. Well, no two trees have the same starting point, and every tree has a unique ending point if it's pushed down to the right. So all trees are either pushed down to the right or to the left, which means we can just push them all to the right and then flip all of our coordinates and push them to the left. So this is just a DAG, and then we can find the longest path in a DAG. And I think I'll just use hash maps, to be honest, because it's pretty easy. Both trees are cut down, so they fall to the right. Okay, let's look at the first case. So here's 0, height 5, height 4. The answer is 9. Yeah, okay. So everything falls to the right. And it's okay to overlap trees. So we're fine there. 0, 5, 9, 3, 2, 6. So you could do 2 plus 6 is not 9. Uh-oh. The answer here is, wait. 2 plus 6. What is 2 plus 6? It's not 9. Oh, maybe you go left here. Oh, wait. Yeah, that's not true. You can have, like this. They can... Okay, well, yeah. So we can do this a bunch of ways. One way is we can do a DP going left. We could say the farthest you can get at each position, assuming the trees fall to the right. And then we can process that from right to left. And we can do the same thing going left to right. And now we would need to combine two intervals that end at the same point. Alternatively, we just care about like the maximum. So it's going to be just one thing going this way, one thing going this way. We just care about the maximum ones that can land at each position. So that shouldn't be too bad either. Yeah, maybe let's just start typing and then figure it out as we go. You know what, that's actually a terrible strategy. Let's not do that. So we have a bunch of trees. We have a bunch of, they can each fall in two directions. So first we'll like process everything falling left. And we'll get the maximum distance each tree can fall. And then we can do the same thing going right. Get the maximum distance each tree can fall. And also where it ends. So now when you're going right, the maximum distance you can fall is either you land and you continue going, or you land at someone who fell left and then continue going that way. Yeah, so we'll do two sweeps through it, through the array. Okay. So this is called timber. We'll fix the file name later. So this looks like int n equals this. Yeah, okay. Static class tree elements comparable other trees. Int x height of the tree, x height, static x, this dot height was height. They all have distinct x's. We just need to compare their x's, that will sort them. We have an array of trees. And we'll read all of them in. And then we'll sort them. And then they're sorted by x. Okay, so our first sweep will be assuming everything falls left. So hash map integer fall left at new hash map integer these need to be long. Oh, they can probably actually be integers. Let's make them longs just in case. Alright, so now for int I equals n minus 1, I squared equals to 0, I plus plus. Int additional, or long additional, equals fall left at dot get or default. So we want to fall at trees at I dot x, and the default value will be 0. 0 long. So this is how many additional things we can get from people falling straight into us. And now we need to update this. So fall left at trees at I dot x minus trees at I dot height dot, well, yeah, okay, long new val equals this. Old val equals trees fall or trees left at dot get fall left at getter default at index get 0, and then the new value will be the height plus trees at I dot height, or no, plus the previous value, additional. Okay. So now fall left at dot put trees at I dot x minus trees at I dot height. Put the math dot max and new val and old val. Okay. Long answer equals 0. Answer equals math dot max. And the old, or well, and new val, I guess, right? Because that's the only new thing. The old thing we already know about. Okay, and now print the answer. So that's everything falling left. Now we also need to consider falling to the right. Do we also want to sweep from right to left here? I suppose it doesn't hurt. I'll make another hash map. Okay, additional equals, yeah, this math dot max of fall left at, well, let's just do it simply, right? So fall left, or fall right at dot get trees at I dot x plus trees at I dot height. Get 0 by default. Additional equals math dot max of additional and fall left at dot get or default trees at I dot x plus trees at I dot height 0 by default. Additional, yep, okay. So then the new value will be our height plus additional. Okay. And the old value will be get at our x coordinate. And then fall left at, so this is fall right at now, because we're falling to the right. Dot put at our x, the max of the new value and the old value, and then answer equals math dot max with the new value. So the question of the day is, does this work? It does not work by any sense of the word. Array index out of bounds exception. Trees at I. I do not want to be incrementing, I want to be decrementing. that's fine. 9, 9, 6, 12, 33, 80, 56, a very big number. Looks good to me. Get me the data, please. So we'll copy that, paste it here, copy its file name, paste its file name, generate the answer, get the answer, and submit the answer. It looks like we got it. Download the grading input file, please. Thank you. We will copy that, paste it here, delete the validation text, generate the answer. Uh-oh, why is it so slow? We might have a problem. Oh, that took way too long. Is it just like a massive file? Guess they just have some big cases in there. Well, that's fine. Our code should still work, right? Because I don't think we ever overflow longs. The great part about this is that we have 6 minutes to check. So we might as well just do that. Do any of these things get big? Yeah, it looks fine. I don't know. Right, none of them are really even bigger than 10 to the 9th, right? So it shouldn't be overflowing, because also all coordinates are relatively small. Yeah, I think that's fine. If there were negative numbers, that might be of concern. But there aren't. So let's get our output. It's not alchemy, it's timber.out. Let's get our source code, which is timber.java. We can submit that. Processing my submission. We will know at the end of the round. All right. See, okay, this is very annoying. Whoever designed this website, you put a little red thing here, makes me click it. So I've clicked it. But now I want to go read the next problem, because after I solve a problem, I usually want to read the next one. Which means when I click this next one, now I'm at the submission page, and I want to be at the problem page. So either don't put the little submission icon to make me click it, or let me go back to the problem page when I click the next problem. It's very annoying. Anyway. Okay, with that said, terrific job on the new website. So much better than the old one. Everything looks pretty. It's not just like a unformatted text file. So a very good job, Facebook, in the new site. It's also like a really slick header. It's not blue, it's white. It's nice. Like it. So whatever this font is nice. Okay, anyway, enough philosophy, as Peter says. This problem shares similarities with chapter 2, so since we're not in a rush, I'll probably read both of them. And then see what I want to solve. You've just landed yourself a gig as a delivery driver for a nationwide supply chain. You've been assigned a series of long-haul jobs, so it's time to get to work. For each job, you will be provided with a map of the relevant region, which includes N cities, numbered 1 to N, and N-1 bidirectional roads connecting them. The cities are connected by roads in a single line. Okay, that's probably the difference. It's a tree rooted at 1. There you go. So we do it either on a line or on a tree. Such that there's a road between every 2 pair of cities. In other words, cities I and J are directly... Do they bold the difference? They don't. But that would be... I mean, I guess they do in this case, but it would be nice if in general they did that. That's a smart thing to do. Yeah, okay, thank you. You will begin in City 1 with a shipment of supplies to be delivered to City N, with a full gas tank having capacity of M gallons. You will then have two options at each point in time. Drive along the road from your current city to an adjacent one using 1 gallon of gas. You may not do this if your tank is empty, but it's fine if your tank becomes empty as the result. Fill up your tank back up to M gallons of gas at the cost of this many dollars, where I is your current city. Note the cost is independent of how much gas you had in your tank before refueling. You may not do this if City I has no gas station. So if it's 0, you can't do it. Determine the minimum cost required to arrive at City N, if it's possible at all. This sounds like a very easy DP. Well, not very easy, but rather easy. You can do it with a min Q. Let's read problem D2. Might be more interesting. So I think it's the same problem, except on a tree. Map is organized as a tree rooted at City 1. You will begin with a shipment of supplies to be delivered to another City A. Are there queries, or is it just one thing? Looks like just one thing, because there's only one output per case. Driving along a road, if it's current city, is the input 10 to the 6th still? Yeah, 10 to the 6th. So you have City A, you have a shipment of supplies to be delivered to another City B. And with a full gas tank of this, you have too many options. Drive along your current road to an adjacent one. Fill up your tank. Yeah, okay, same thing. So same problem, but on a tree. Well, if it's on an array, it's a DP, and it's very easy. Because you only drive to the right. Now, if it's on a tree, the only reason you would drive down a subtree that isn't the right subtree, that isn't the correct subtree, would be if you need to get more gas. Well, no, initially, well, when you're at the root, you only drive down the correct subtree. So that's fine. Oh, except you start at A, right? You're given City A. Well, I could just make it start at the root, but whatever. So we start at City A. The first move is 100% going to be towards City B. But after that, it might not be. Maybe let's have a picture. Hello. Alright, so you've got a tree. Oh, you know what? It might be helpful to think about this as, instead of a tree, maybe we have some path that we definitely want to go down. So if we are going from this node to this node, the path is interesting. And in each of these subtrees, you're only ever going to go to one node in the subtree. Doesn't make sense to go to two nodes in the same subtree. Because if you go down to this subtree in order to get gas, in order to go farther down, you're going to use all that gas up on the way back. So it's not super helpful at all. which means you just have these gas stations, but instead they're at like this extra distance, right? So you can think about it as having a gas station where you pay a different amount for each gas station, but you also get a different amount of fuel. So we can effectively turn it into just a line problem where you pay different amounts, but you also get different amounts of fuel. Let's not draw this as a tree then, let's draw it as a line, because that's what we've simplified it down to. So maybe I'll make it red. So here is the interesting part of the problem. So we've got these nodes in the tree, and we've got maybe some other nodes here. And now we want to know where we are here. So if we're here, it only makes sense to go farther right. Because if this, like, let's say we're considering hitting some node that's like off this path, either, like, in order to do this, well, we're kind of like overlapping paths here. So we're going down to here, and now we're going up to here, and now we're going back to here. So, like, if we go down to this node, the only reason we would do that is if it were cheaper than going up to this node, which means this needs to be a very far distance. But if this is a very far distance, then it would be better for us to just keep going on our journey from this node here. So we only move right in this tree, which means we can also do a DP of a very similar nature here by just processing the nodes like this. So that's the idea. And now we can use a segment tree to do range min. And we can also do a multi-source BFS from this red thing. So the BFS will store, or I guess we could just do a DFS. That would be easier to code. The DFS stores where you're from and what the parent is, because it's a tree. Okay, so we can do segment tree range min because we can't really use a min queue anymore since these values change. You might be able to use like a min deck if those even exist. But the log factor is fine for us. Shouldn't be too tight of a time constraint. So this is the solution, segment tree range min, to speed up the DP. And then we can do two, I guess just DFSs. We'll have a DFS coded. Yeah, if we have a DFS coded, we can have just two DFSs from these two nodes, and that will let us find the path between them. So then from each node in the path, we'll do some other DFS, ignoring other nodes on the path, to get all of these nodes. Then we can sort all of the nodes first by their left to right distance. Yeah, okay, we can do that. It's going to take a bit of coding, but I think that's fine. What is this called? It's called running on fumes. Let's just call it fumes. All right. So first we're given the number of nodes. Then we're going to need node class. Public void DFS on node from. Which node we're from, or this is the parent, I guess. Okay, now we also are probably going to want to sort these nodes later on. So int distance, distance. We'll also have a dist from A and dist from B. Okay, and then a Boolean marked. Or like on path, how about that? So we know whether it's on the path. So first we'll do a DFS from some parent and then in some distance. Dist equals dist. And then for node and then in our adjacency nodes, we want to DFS from that. It's one farther away. And then we're fine. So that should be enough to get the path. Okay, so now, how is this input given? So we're given, what is M? Is this multi-queries? Oh, the capacity, okay. So int tank capacity equals this. It's given before everything else. We're also given A and B. All right, are A and B between 1 and n? Yeah, okay. So int, from equals this, 2 equals this. All right, so now we need to read in, are we given a bunch of edges? We're not given edges, we're given this weird way of reading in a tree from like 1987. I've forgotten how they like to do this. The parent and the cost of the edge. Wait, do edges have cost? Oh no, yeah, okay. So this has a refueling station as well. Okay, so int gas cost. Does the root not have a the root is 0, so it just doesn't have a parent? Yeah, okay. That's fine. Okay, so if pair is equal to or is not equal to 0, then node other equals nodes at pair dot adjacency dot add nodes at I. So make these 2, okay. And now nodes at I dot cost equals cost. Good. So we have all of this figured out. We've read input. Most difficult part of the problem. Well, not really. This is actually an interesting problem, so we'll see. So now we want to update. We want to find the path between them. Nodes at from dot DFS from, there is no parent, and the distance is 0. And for each node, nn dot distance from A equals nn dot dist. Then we want to DFS from B. B equals nn dot dist. Okay. So now for node nn in nodes, nn dot on path equals nn dot dist A plus nn dot dist B equals nodes at from dot dist B. So now we know the things that are on the path. We should probably, yeah, okay, so now we need to do some other DFS. public void dfs2 node pair int dist from. Oh wait, ooh. It doesn't even matter. Yeah, it doesn't even matter what it connects to. Oh, it doesn't even matter what it connects to. Shouldn't even matter what it connects to, because it's yeah, we can just sort these. Like, we know the distance from the path. Like, we can figure that out just given dist A and dist B. We know the things that we care about. So now we just need our seg tree. Leftmost equals leftmost, star rightmost equals rightmost. If L child is not equal to, or if leftmost is not equal to rightmost, then L child equals new seg tree from leftmost to mid. R child equals new seg tree from mid plus 1 to rightmost, and then mid equals leftmost plus rightmost. Void update int index int value. So we want the min cost. Yeah, okay. So min equals integer dot max value. This dot min equals math dot min. Min and value. If leftmost equals rightmost, return. If index less than equal to L child dot rightmost, then L child dot update. Otherwise, R child dot update. Then we need a range query, public void range query, int from int2 or int L R. L is less than equal to leftmost, and R is greater than equal to rightmost. Then return min if L is greater than rightmost or R is less than leftmost. This returns an int. Ooh, we should probably return a long, right? Because the costs can probably be rather large. The bounds cost up to 10 to the 9. Might take a bunch of time to do that. So this needs to be a long. This needs to be long.max value. This needs to be a long as well. This needs to return a long. Return long.max value. Return math.min, lchild.range query, and rchild.range query. Okay, cool. So we have our range query segment tree. Nice. Okay. Seg tree st, seg tree. So it'll go from 0, and then the farthest part on it will be nodes at from dot dist b. So it ranges through the whole range, I guess. Can the answer be 0? -1 presumably means it's impossible. Okay. So we should sort the nodes by distance from the right child. Oh, no, not the segment tree, the nodes. Good, and then public compare to node O, return integer integer dot compare dist b o dot dist b. All right then. So yeah, we can do right to left. So arrays.sort nodes. Ooh, we need to store which node we're from. Yeah. From I to I. Node from equals nodes at from I to equals nodes at to I. Now I'm safe to sort. Yeah, okay. So we've got this segment tree. Okay. Yeah. Okay. So now we sort them and we want to process them from right to left. It doesn't actually matter whether we tie break, I don't think, because it shouldn't matter. So for node, or wait, they're sorted by distance from the right, so we can just go in increasing order. So for node and then in nodes. And we can do this, so we can say or what do we want to do? We want to say the DP cost at a certain node. Yeah, okay, so let's say whether it's got a, whether you can buy it there. So Boolean can buy equals false. If cost is not equal to 0, nodes at I that can buy equals true. But also nodes at from that can buy equals true, and nodes at from that cost is equal to 0. Pretty much you can just do that for free. You just get free gas there because you start there, and why would you drive backwards? It's just unhelpful. You've got a full gas tank anyway. Good. So now we want to do this DP. So the answer will be nn dot, or plus it'll be from dot dp answer. That's the answer. Okay. So if we're processing them from right to left, then we don't really need to worry about the left endpoint because we won't have processed that stuff yet. So that's not an issue. Okay, so now we're going through each node. We need to update the segment tree. So st at from or dot update from dot distb cause 0 to finish from there because we're already at the finish. So that's free. Okay. So now, yeah, okay. So we should also worry about if it's out of the range. So if index is less than leftmost or index greater than rightmost, and return. So now we want to process this node. So I suppose we should include the cost of buying the gas in this node. So we can just make can from ever equal to? We can't. Okay, so 2.canBuy equals false. It doesn't matter what its gas cost is. So if nn dot can buy, well, if it can't buy, then we should just continue. Otherwise, we need to query the future best cost. So yeah, so how do we do this? So we want to query from the length of the path. That's how many nodes we can get. Tank cap is the distance. So the left int L will be equal to nn dot dist b. Oh, I guess it'll be from dot dist b minus this distance. So that'll be the left endpoint. The right endpoint will be L plus the gas cost, or plus the tank cap. So that's how far we can drive. Now the long answer will be equal to the min from L to R, that's the min dp value, plus the cost of this node. Okay, and now we need to update the segment tree. So now st.update. The index will be nn.distb, or no, it'll be .dist a. Yeah, that's how far you need to be. Okay, the value will be the answer. Should be right. And now we need to say nn.dp answer equal to the answer. So I think that's fine. Let's test it. Okay, kind of as expected. What is the first case? So let's draw this out. So we have four nodes. Wait, what is this first index? Is this 4? How is input read? Oh yeah, 4 nodes. M is 1. Gas capacity is 1. Go from 2 to 3. Okay, so you have 0. So this is node 1. Then node 2 has a parent of 4. And 3 also has a parent of 4. And 4 is a parent of 1. Okay. So then this is $20. Let's use a different color. $20 here. $30 here. And $40 here. Okay. We understand the problem. Array index out of bounds exception, index 4 out of bounds. Equal to -1, and this is 1 based. Okay, that looks like Stack Overflow. That's fine. How about we just get the first test case? You know, that would be probably a good idea. Duh. If nn is not equal to the parent. If we're equal to the parent, then we have created a problem. The answer is 40. By golly, that's right. 40, 60, 20, 104, 17. Okay, so our infinity is too big, because we're getting our infinity and we're adding to it. Static long infinity equals long, or equals long 1e18. So this should just be infinity, not actually that number. This should also just be infinity. And now we have our answer. So, yeah, okay, is this a problem? We're taking this infinity, adding some number. Okay, so long real ants equals from .dp ants is greater than or equal to infinity. If it is, return -1, otherwise return real answer. Nope. From .dp answer. Okay, that looks fine. Now this will crash if I do it on actual data. So what we need to do is we need to do the thread trick. Thread t equals new thread, null, string, 1 left shift 28. Okay, that's fine. Public void run. Do the stuff, please. And then t.start, t.join. Okay. Unexpected error. What is the unexpected error? Why do we have an unexpected error? Oh, yep. Cool, looks good. So now we want to submit this. Oh, poof, this is, let's try it in this sample first, just for sanity. Oh, did they change the input format? Oh, that's annoying. Fine. Let's just try this. Okay, download the validation input. Save. This, I will take that. I'll put it here. Copy the name. Rename it. It's a very long input name, that's fine. Give me the answer, please. There's the answer. Choose file. We would like running on fumes, validation, input, output. Validate. We got it, all right. Give me this, please. Thank you. We'll take this input, put it in the real folder. Oh. Okay. Remove the validation substring. Run that. Give it a minute to think. Alright. Everything seems okay there. So we can take the running on fumes chapter 2, no validation output. Cool. Then our source code is this, fumes, right? Yes, fumes. Processing your submission. All right, let me know when you're done. Okay. See, this is just obnoxious, please. Thank you. Okay. All right, so now time to figure out how to do this without a tree. Blah, 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 blah. Okay, so you're given, for each job, there's a line containing space-separated integers n and m. M is the, yeah, okay. Then n lines follow, the ith of which contains integers ci. Yeah, I see. So this is just the ci rather than the parent. So let's make another version of this. Fumes 2. And cool, well, we'll leave that. So now the parent will simply be, parent of node I will be I minus 1. And you're trying to go from node 1 to n, right? In this version? Yeah, you want to go to city n. Okay, so we can just ignore this. So int from I equals 0 to I equals n. Minus 1. Very good. Okay, so everything seems to check out. Do we pass samples? Because that would be nice, wouldn't it? 20, 30, negative 1, 165, 0, 50, 19. Okay, I buy it. So this needs to be true now. We're submitting. And get me the code, or the file. Thank you. We're in submit mode. Submit my stuff. Good. Okay. Now here is my output. One validation output. Submit. Okay, I got that part right. And the full grading input. Save the input. I'll take that. Thank you very much. One input. The output. Looks good. Here is the wait, no, it's running on fumes, chapter 1 input dot out. Okay, my sample code is fumes 2. Yep. All right, so well, I've submitted to everything, and I think that's where I'm gonna leave it. So we'll go over solutions too, don't worry. But yeah, what friends of mine are doing this? Let's see. Nick Wu, Geothermal, Ben Q, Eknerwalla. Oh wait, can we do our nickname? Is that a thing we can do? Oh, Raj, come on, man. How do you do our nickname? Is that let me figure that out real quick. Display handle, so good. Thank you. This is amazing. I love that. Well, there's my public email for everybody in the internet. Oh well. Yeah, there's my address. Yeah. Okay. Well, on the bright side, now you can see that I'm second thread. That's fantastic. I love it. All right. Cool. Looks good. So It's pretty much kind of how you might expect, I think. Let's talk about solutions. So I'm gonna do a quick refresher here for all of the problems in case you missed them. And again, obviously this will not be published until the contest is over, because I don't want to cheat. But we'll talk about it. All right. Problem A: travel restrictions. 2020 has been a tough year. Yeah, so you've got a bunch of travel restrictions. So basically, you have you've got like some nodes in a line, and some nodes you can't enter, and some nodes you can't exit. So maybe this node you can't enter, maybe this node you can't exit, and stuff like that. So now you want to see what pairs of nodes can you go from and to. What we can do is we can build a graph from this. So a graph in computer science, you've got a bunch of nodes and a bunch of edges. And we can add an edge between two nodes if you're allowed to, like a directed edge. If, like for this node, you can't add any outgoing edges from it because you can't exit it. But from this node here, you are allowed to exit it, and you are allowed to enter this node. So we can add this edge here. And the edges are only going to be between pairs of adjacent nodes. So this node here, you can exit it, so you add this edge here. You can also exit this node and enter this node. Here we have two edges like that. Here we also have two edges. And you can't enter this node, but you can exit this node. So you can make an edge like that. You can also add this edge here. So here this would be our graph. And once we have our graph, we can run just Floyd-Warshall's algorithm on it. And we can see the shortest path between all nodes, or we can also see whether it's traversable between all nodes. So Floyd-Warshall's is like a good thing to learn. It's very, very easy. You just do these 3 for loops, k, I, j, and you just try going from, if you want to go from I to j, you just try all intermediate nodes in between them. So this is the code for it. It's 4 lines, I guess. It's that easy. You remember the order of these loops, you're set. Otherwise, you can do an end to the 6th, and that'll probably be fine too. You do like A, B, C, B, C, B, I think? Or what would it be? It would be, well, it doesn't matter. You can do end of the 6th, that's fine. Or maybe it's end of the 7th, I don't really remember. Anyway, yeah, Floyd-Warshall's. You can also do better stuff, probably, but I didn't really feel like trying that, since n was so small. The problem was easy anyway. Alright, problem B, alchemy. So this was a very easy problem, but the proof for it is rather interesting, I think. So let's talk about that. What you can do is if you have a series of stones, maybe some are red and some are blue, what you can do is you can maybe like pick any group of 3 stones, like this here, and you can combine these into the majority of them. So we can turn this into a red. We could also combine these 3 stones and turn these into a blue. You want to do this as many times as possible, and you want to see if when you're done, you will have exactly 1 stone remaining. Oh, wait a minute. Yeah, no, that's fine. So here's the thing to keep in mind. Every time you do this operation, you delete exactly 1 red and 1 blue node. Or 1 red stone and 1 blue stone. So it doesn't really matter what you do. It also doesn't matter the orientation of these stones. So you can do them always adjacent. I don't know if you even need to in the problem. Maybe they don't have to be adjacent in the problem. But, like, it doesn't matter. So what we'll do is we'll take the first time that there's a blue stone, and then the first time there's a red stone or whatever, and we'll find some group that intersects this red and the blue. So every time we have a red and a blue next to each other, we can delete these 2 and then replace it with just this. And we can keep doing this as long as we have a red and a blue next to each other. So we can delete these 2, and now these 2 are adjacent, so we'll delete these 2. And now we're left with 2 reds. So if you're left with anything else, then that's impossible. Like, it's not going to work. So the solution is, all that matters is the number of reds and the number of blues. And if every time we delete a pair, because we're always allowed to delete a pair, because there will always be some third element there. If every time we delete a pair, then we have 1 element left over. Or we'll pick 3 numbers and then we'll keep 1 left over. We just care about, is there exactly 1 more red than blue or exactly 1 more blue than red? If either of those are true, then we can be left with just one stone. Otherwise, it's impossible. It's problem B. Problem C, timber. So yeah, this was, I don't know, maybe like a real problem, but it got a little annoying to implement. It wasn't too bad. The idea is you have a bunch of trees, and they would kind of fall down right about as you would expect. So maybe you've got like some tree like this. They're just really line segments, kind of. Maybe some tree like this. Maybe you have a tree like this, and then another tree like this, or something. So if you knock this tree down to the left, it'll land like that, and you'll have a line segment here. Maybe you knock this tree down to the left, and it falls like this. You have a line segment here. If you knock this down to the left, you would have this line segment here. And if you knock this down to the left, you've got like some line segment like this. So what you're looking for is, let me erase some of this because it's not super helpful. But if we knock these three trees down all to the left, then what we get is this continuous range where you have trees along the entire range and no part of the range is too thick, like has a thickness of 2. This is what we're looking for. We want to see what's the longest possible thing that you can get that looks like this. Now, one helpful thing to look at is since no two trees have the same position, you can't have one tree knocked down to the left and then another tree knocked down to the right on the same position and count both of these. That's not allowed. Which makes it easier because then we know our answer is going to be of the following form. We'll have a bunch of trees over here and all of these get knocked down to the right. Let me move this so it actually looks better. Yeah, we'll have something like that. These all get knocked one way. Then we'll also have something like this, maybe. Oh, sorry. So this gets knocked over here. This gets knocked here. Maybe this one gets knocked here. So we'll have a bunch of things that fall one way, a bunch of things that fall the other. What we can do is first we can process all of the trees that get knocked left, or we can process every tree and consider what if this tree gets knocked left. And we can do a DP where we store, for a given index, how long of a continuous range can we get going to the right. So we can use like a hash map to do this if the values are big. If the values are small, you can just use an array. Let's actually just check, do we even need a hash map? Yeah, it looks like values get pretty big, so it might be helpful to use a hash map. 10 to the 9th memory is quite a bit of memory for an array. So hash map it is, or map in C++. Or you can use a tree map in Java, whatever you feel like. And we want to like update this value in the array. We can process the trees from right to left if they're falling left. And then we can update this value in the array, and then we can update this value in the array. To update a given position in the array, what we do is we just query what's the farthest you could have gotten and ended here. And then we also need to consider, okay, well for ourselves, we have this maximal length, and then we can add ourselves to it, and we can also update this position in the array. So that's how you do your sweep going left. Now the sweep going right is very similar. The indices are just slightly different. So here we're going to update this position here, and we consider looking at this position here. And we look at this from either a range that has just fallen left, or a range that's about to continue falling right. You can probably combine these into the same type of cases, because really all of these things are just like a line segment. Right, this is just a line segment. You just have to be careful not to consider the same tree twice. Yeah. I guess that's it. So, yeah, the TLDR is like we can do one sweep going left and considering like ending at this point. And then we can do another sweep going right, where we say, like we consider the things like this. And then we say, okay, if you end here, what's the farthest you can get? So yeah, alternatively, I guess what you could do is you could just turn all of these things into ranges. So you could make one range like this, and then make another range like this. And then you could just find what's the biggest the ranges can be in their entirety. That way you don't have to do 2 sweeps or even worry about left and right. So it should be actually quite easy to implement if you do it like that. My way wasn't too bad, but could have been cleaned up a bit. Very cool. So now, what else do we have? We've got just this problem D. So I guess I'll talk about problem D1 first. That might make explaining D2 easier. The idea behind D1 is you have some number line, or some series of positions that are all in a row. And you start here, and then you want to get to position N. Start at position 1, want to get to position N. And you've got several gas stations along the way, so maybe you can buy stuff for like $30 here. You can buy stuff for $100 here, or you can buy stuff for $10 here. And you can also only go so many positions before getting gas. So maybe you can go, you can travel 3 units before you get gas. So one option would be you could travel these 3 units. You could buy gas here for $100, and then you could travel 3 more units like that. That would be one way of doing it for $100. You could do it for cheaper though. You could travel like that. Now you pay $30 of gas, travel here, now you pay another 10, and then travel here. And there you go. That's how you do it for $40. So what you can do here is we can do a DP, DP at some index, and this will store the min cost, or min cost to get to the finish. If we buy gas at index. So what we want to do is, in order to actually calculate this DP, it's really helpful for us to we want to do, like, we have a bunch of indices, and now these are kind of wobbly. Oops. If we want to calculate the answer for this position, then we want to consider all of the positions we could reach if we bought gas here. We want to consider all of the positions that we could reach, and we want to take the minimum of all of them. And then after we do that, we add the cost of getting gas here. So if we want to take a range min in some array, we can use a segment tree to do that. So this is like a segment tree range min. I'm not going to explain what a segment tree is. There's a algorithms thread video on that if you're interested. It's also got some hard problems, so maybe I'll link that in the description. But yeah, so you're looking for segment tree range min, and then that's how you can do this DP. So you can do this DP in n times log n. Now you can do even better. You can do this in just order n actually. I won't cover all of the details for that, but you can abuse the fact that this range is always a fixed size. So since you know how long this range is going to be, you can use this thing called a min queue. And this is a good topic for an algorithms thread in the future, because I haven't ever really explained this. But you can use a min queue, and then you can do it in linear time instead of n log n. But n log n is certainly fine, right? There's no problem with that. Okay, cool. So that's the idea behind this first div1d, or not div1d, hacker cut problem D. Now for D2, it's a little bit more tricky, because now instead of having some like just array that you're doing this on, now you're doing this operation on a tree, which might make it a little bit more tricky. It's not super obvious, I guess, whether it does or not. It turns out it doesn't once you do some simplification. But yeah, you might have a tree that looks like this. And now you have 2 nodes on the tree. You want to go from this node to maybe this node. So you also have places that you can buy gas. So maybe you can buy it here for $30. You can buy it here for $100. And you can buy it here for 10. And again, maybe you can travel 3 units as well. Or let's say you can travel, well, let's say, let's move the 100 somewhere else. Well, I don't know. Yeah, it doesn't matter. So the idea is, what you might want to do sometimes here is you might want to go off, like, to get some gas somewhere. Then you might want to come back on this interesting path, the shortest path here, in order to keep going to the finish line. And that makes it a bit harder because it's not just a problem on a line anymore. Well, we can make this problem a bit easier by noticing the following thing. So let's consider this path here between the 2 nodes. This is like an interesting path because this is like the shortest path that we want to take, but we don't necessarily want to take only nodes on this path. We can make some observation though, which is we only want to take, like, if you look at this tree that's rooted at one of these nodes here, Really, we can look at like all things that are connected to this. So it's like this group because they're all rooted at like this node. We only ever want to visit one gas station in this entire group. If we visit a gas station, we want to do that because this will help us go to future gas stations later on. But it's never beneficial for us to visit two different gas stations. If we visit this first one, and maybe we visit this first one in order to visit the second one here, because maybe we would like maybe this one is cheaper, but we would want to go to this top one first in order to get more gas in order to get to the bottom one, because we wouldn't be able to reach the bottom one otherwise maybe. Once we have filled up our tank here, we might as well just continue going along the path. There's no reason to go down to this lower node because like we'll have less distance we can go from the lower node and we'll spend more money. So we only want to visit any one node in the subtree. We don't know what the optimal node is, but it won't be multiple nodes in the subtree. The other thing to keep in mind is once we go across some edge here in the shortest path, we never go back. So we're only going straight to the right and we only visit one node in each subtree. Why would you not want to do that? Well, I had a good example in contest, so I'll kind of draw something else like that again. But if you have this path here, maybe you want to come down here to some path like this, visit this gas station node, and then you want to come back and you want to visit this gas station node. So maybe you think that this is like the optimal thing to do, going like that, then you go up like this here, and now on the third turn you go back over like this. So the only reason, like if we want to visit this node, the only reason we would visit this bottom node first is if we weren't able to reach this first node on our initial tank of gas. What that means is this path needs to be really long. It's got to be longer than this path. But here's the thing. If this path is longer, in order for us to not want to just go there initially, right? Because otherwise, if it were short, we could just take this path. But if this path is really long, then it's not beneficial for us to go like this, when instead we could have just taken this path. So basically, like there's no reason to ever go back in this array. It's never helpful. Which means now we have the ordering of processing this DP, and we can process it in this order. We can process this node first, then like this node, then the children of this node, then this node here, then the children of this node, then this node here, the children of this node, and we can keep going. And we know none of the children within the subtree will care about each other at all. So yeah, so when we do this, we can like process things in this order. We still have to optimize our transition a bit though, because currently it takes like linear time to check all of the things that it can reach. We can do better than that because we know like everything else is going to be like some other node that we can reach somewhere later. So we want to look at some continuous range here. Again, we can use a segment tree in a very similar way. There's a short difference though that we have to keep in mind, which is like if we have some node that's like down here, right? So maybe it's 2 positions down. Then whatever, also this would have to be longer in order for this to be relevant, but that doesn't really matter. So now we need to consider like how far of a range we can go. And maybe initially we have a gas range of like 4, right? So we can visit these 4 nodes or something. Or maybe it's 3, this would be 3. But instead, since we have to spend 2 units going up here, then we have to decrease the range in the segment tree that we query by that amount. And this is like actually pretty easy to figure out with math. So you can figure it out if you know this distance here, and you know this distance here, and this distance here, then you've just double counted this twice. So you can get it with math pretty easily. But yeah, we just want to do a segment tree query on this part of the array, right? We can even query this because we know we won't have filled all of these in yet, so these will all be infinity. So that's very easy. We just do a prefix segment tree query. And after we do that, we want to update our answer. Now, it's a bit tricky to update the answer as well, because we know how far it would take to finish this, right? But if someone's trying to get here, this isn't the same as getting to node 6. Actually, it turns out this is the same as getting to node 2. Because you have to go to node 6, and then you have to go 2 farther, which is the same as going 2 down here. So instead of updating position 6 in the segment tree, we would actually update position 2. And then you have to like min it with the previous answer for position 2. That's not a hard thing to do. You just, instead of your update being like point set, you have point min width. All right, so that's problem D2. I guess that's all of them for the Hacker qualification round. I enjoyed the problems. I thought they were all good. I thought B was definitely easier than A, I guess, or less code maybe. Maybe A was pretty classic, and that's why they put it in the beginning. But yeah, I enjoyed it. Hope you enjoyed as well. And I guess I hope I qualified. It's possible I got every problem wrong. That would have been kind of surprising. But yeah, I hope you qualified as well. And hopefully I'm also allowed to compete in round 1. We'll see. But if I am, I'll see you on the scoreboard. That's all. Goodbye.